Welcome to the Grandmaster Series. I'm your host, the sometimes repetitive, but never redundant Jim Scott. Today on the Grandmaster Series, because we're feeling a bit indecisive, we'll be continuously scrolling to the right to find something good to share with you. Wait, what? Wait, we're talking about building better recommendation systems so that I don't have to continuously scroll to the right? Well, this is great. This should turn out to be an incredible time saver for me. Now I'm really excited about today's episode. We'll be speaking with the world's leading experts in data science. We'll explore their approach to the Booking.com data challenge and learn how to build a winning deep learning powered recommender system. There's just a few things I'd like to point out before we get started. Anything discussed today, which is publicly available, will be shared in the video summary below. If you have any questions during the video, you can submit them through the chat. We'll try to provide answers throughout and at the end of the episode. We'll be sharing some links below to a 3-part blog series detailing how to build a winning recommendation system. And finally, please be sure to subscribe to our channel to be notified of upcoming videos in the Grandmaster series. Now I'd like to take a chance to introduce the team. First, we have Chris Diott, Senior Data Scientist at NVIDIA. Chris has a PhD in computational science and mathematics with a thesis on optimizing parallel processing. He is also a 4x Kaggle Grandmaster. Next, we have Jean-Francois Puget. He holds a PhD in machine learning and has published over 70 scientific papers in peer-reviewed conferences and journals. He is a 2x Kaggle Grandmaster. Next, we have Jiwei Liu, Senior Data Scientist at NVIDIA, working on AI infrastructure, including Rapids. He has a PhD from the University of Pittsburgh in electrical and computer engineering and is a Kaggle Grandmaster specialized in tabular data modeling. And lastly, we have Gabriel Moreira, senior researcher at NVIDIA working on deep learning for recommender systems, which happens to be the focus of his PhD. In this episode, Chris will kick us off and will provide a bit of background on the competition. Now that the stage is set, I'd like to hand it over to Chris. I'll be back at the end for some Q&A. Chris, it's all yours.
Thanks for the introduction, Jim. We got an exciting episode today. This is the 5th episode of the Grandmaster series, and today we're doing something a little different. The Kaggle Grandmasters of NVIDIA have teamed up with NVIDIA recommender system experts from the Merlin team, and we'll be discussing a competition that we competed in together, which was off of Kaggle, and we took first place, and we will be describing our solution. So the top right four names, those are the Kaggle Grandmasters of NVIDIA, and the other 3 names are the NVIDIA recommender system experts from the Merlin team. The competition we'll be discussing today is the Booking.com data challenge. So it's part of ACM's 14th annual WSDM conference and workshop. And the nature of the challenge is to predict. So, given a user and a sequence of cities, hotels they've made reservations in, we need to predict where their next city they will be visiting in. So, the training data set gives us 200,000 trips where we have the full information, and then what we're asked to do is for 68,000 trips. We don't have the last city, and we're asked to look at the beginning cities and then predict what the last city will be. And the way it's evaluated is our models can make 4 predictions for each trip. And then if any of those 4 predictions are correct, then we say we got that trip correct. And then our score is just the percentage of trips we got correct. So this competition lasted for about 2 months. It was at the beginning of this year. Here's a timeline. So you can see we joined late. We hopped in 2 weeks before the ending. And in this competition, something that was unique is you only allowed 2 submissions. So you, of course, make your final submission at the end. And then 2 weeks before the competition ends, you're allowed to make a practice submission to sort of test how well you're doing. So we had 1 day to do that. So we stayed up late and we built a preliminary model in a day, and then we worked hard for 2 weeks to build our final model. And you could see our hard work paid off on the final leaderboard results on the right. You could see at the top, we got NVIDIA Rapids AI. Our model's accuracy was 59.4%. So in black here, here's a sample of what the data looked like. So each row is a specific hotel booking, and it tells you which city the booking was in. It tells you the check-in, check-out date, the user's ID, which user made it, and which trip it was part of. And you can notice that all the information, or most of the information, is made anonymous. And some of the challenges were, so the number of cities is 40,000 possible cities. So your model is trying to predict, one city out of 40,000 possible cities. So you see, you can't be successful by purely guessing. Your model really has to analyze and detect the patterns to be able to predict the human behavior. And other challenges I mentioned, were allowed 2 submissions. The data set's pretty large. We've got millions of reservations. And between the train and test data, there's only 15% user overlap. So you can't just sort of memorize a person and just try to tackle the problem like that. So here's some plots of the data to help understand the data. So most of the columns, so the column with the city IDs, as we mentioned, it's actually was sparse. So 10,000 cities only appeared one time in the data set. So it's tricky. So you see, you can't quite build a pattern from only one observation. A lot of the other columns were dense. So most of the columns were categorical features, and for the other columns, the values occurred often in the column. So we would say that they were dense. And it's a sequential recommendation system problem. And one important thing, since it involves time, is you want to compare the train and the test data set. And if you look here, you can see that the data for the train data set was in the same time period as the test data set. So you can see all the reservations are between January of 2016 through March of 2017. The blue line is the counts of the train, and the orange line is the count of the test. And you can see the distribution is the same. So that's good. That makes makes our work a little easier. And here's the properties of the trips. So we can see that most of the, here's a histogram, frequency counts of different trip lengths. And we can see that most of the trips were between 4 and 10 bookings. And here's a histogram of how often users appeared in the data set. And we can, how often a user had a trip in the data set. And we can see that most users had 1 trip, and then some users had a couple trips. So that's some plots of the data. So when we built our models, we put all of the original columns into our models, and then additionally, we engineered some new columns shown in this table here. I'll mention a few. So given the check-in and check-out dates, we built features like which day of week was the booking on, week of year, month, is it a weekend, the length of stay, days since the last booking. And then since it's a sequential problem, we have a history of cities and other information. So we built some sequential features by looking at the previous 5 booked cities and inputted that into our model. Additionally, we computed some trip stats like the number of reservations, the trip duration, reservation order. And then what you're about to see is that our final solution is an ensemble of 3 models. And then all the models use the first 4 rows of features here. And then the third model, which is the transformer model, it used the additional bottom 2 rows of features, where some features were built about user behavior and some features were built about properties of the cities. All right, so that's a summary of the competition, a little bit of a review of what the data looked like. And now Jean-Francois is going to describe our models.
Thank you, Chris. Just a side note, I'm CPMP on Kaggle. If you look for me under my name, you won't find me, but I'm CPMP. So one technique that is used in recommender systems is matrix factorization. So the idea is to represent, say you want to recommend products to people based on their previous buying pattern. One way is to create one vector per product, say of 128 or 64 values, and one vector of same length per user, per person. And you will say that a user is likely to buy a product if the product vector and the user vector look similar. And one way to measure similarity is called cosine similarity. It's a dot product of the vectors. You just multiply the two vector element-wise and take the sum. And this has a nice property that you can train a model to compute vectors in this way. So you create a matrix where columns are users, and rows are products, or you can transpose. And you put a 1 if a user has bought a product so far, and 0 if not. And then you can see if you can find a matrix for the columns and the matrix for the rows, such that when they are multiplied, you get your 0, 1 matrix. If you do this, and this can be done efficiently, then you have the vectors we are discussing. In practice, people don't compute exactly fully the matrix product times users because it can be too large. So they will sample it, but that's the idea. This was state of the art 15 years ago. 15 years ago, there was a contest held by Netflix for improving their recommender system. And matrix factorization was a key part of the winning solution. And from then, you can find it. So you can find it under the name of collaborative filtering. And the idea is people having similar buying patterns will have similar vectors. Same product that are bought by similar people will have similar vectors. So how is this relevant to our problem? As you've seen from the EDA, the data analysis Chris presented, users appear only once for most users. So you cannot create a profile per user. So we had the idea to create a profile per trip, and with the idea that similar trips will end the same way. So here we would replace users by trips and products by city. And then the problem is to, given a trip that went so far, what is the most likely next city? So what city is the most likely to be kind of bought by the trip? That's the analogy. So next slide. So we develop a number of models. Here is the simplest one, and my teammates will present their models after. So we start with a matrix factorization, and we have embeddings for every city. So you see at the bottom left, you have the embedding table. And then the idea was to compute a vector, an embedding for trips, by combining the embeddings of their cities. So we use a city embedding two ways. One directly at the top as the product, and via a neural network to combine them so that we get a representation of the trip. So one model was just to have a concatenation and some dense network to get the trip embedding. We added some of the additional features Chris presented, but that's the main idea. And we see that adding the matrix factorization on top of the dense model improves the by 2% the accuracy, just adding this factorization. Next slide. So that's the final. MLP stands for multi-layer perceptron, or people also say dense network. So the input are the embeddings of the cities of the trip, plus a concatenation of embeddings for the other features. This is moved through a three-layer dense network, and then multiplied with all cities embedding. And this gives you a probability for each city. So the interest of this model is it's very efficient, and its accuracy on this problem was similar to our other models. But it's a well-known, not trick, but a well-known property that we use in Kaggle and in competition in general. Even if you have several models of similar accuracy, combining them will improve the results. So now I will let Jiwei present another model that is different, but with similar accuracy. Jiwei?
Thank you. Yeah, our second model is it's a deep neural network with multi-stage and multi-head, which also uses multi-session-based matrix factorization head. So in the first stage, so when we look at the CD-ID sequence we are given, so the CD-IDs pass through an embedding lookup table, and we use a GRU recurrent neural network to encode the CD sequence. So the output of the last GRU unit summarizes the travel patterns of the given user. So this output of the GRU unit is combined with other features such as day of the week and the Booker entries and so on and so forth. So these concatenated features go through two layers of fully connected layers. And we directly predict the probabilities of the next, actually of the last booking city over all the possible cities. So which is this purple prediction head. So in the first stage, we have the predicted probabilities over all the 40,000 cities. In the second stage, we took the top 50 cities from our prediction, and we fetch the CTIDs of these top 50 predictions. So these top 50 CTIDs go through the embedding table again, and we have their embeddings to represent our top 50 predictions. Next, we took the output of the last fully connected layer. So the output of this layer represents the user behavior. So we calculate the dot product between the top 50 CD embeddings and the output of the last fully connected layer to refine our predictions. So basically, the larger the value represents, more likely the user will book the city. So the stage 3 is similar as stage 2, except that we use the output of the second last fully connected layer and calculate this dot product, so which is essentially a matrix factorization operation. So in the end, we have predictions from the first stage, second stage, and third stage. We use non-negative linear regression to combine the predictions of the three stages and produce the final prediction. So the rationale of such a multi-stage, multi-head model is to mimic traditional workflow of multi-stage recommendation pipeline. So typically, when there are many items to recommend, we typically filter out a small number of candidate items and calculate the ranking of these items against a user vector. So here we use one neural network to do this multi-stage recommendation process, and we could train it from end to end. So in this way, we achieve the performance of such a multi-stage design, but it is also simple to train and deploy. Next, our colleague Gabriel will talk about our transformer-based model. Thank you.
Yeah, so our third model is similar to the previous one, which used GRU, so that you feed data in a sequence to the network, but instead of using a GRU layers, we used transformer architecture. In this case, we used the XLNet transformer architecture, and similarly to the previous works, we have used the session-based matrix factorization head by weight tying the embedding table of the cities and reusing those weights as the output of the network. So in the input, as the previous model, we have the city ID in special, which we share embeddings, which we share weights with the output layer, and we had also some other categorical and continuous features. Then all of them were concatenated and sent through a number of fully connected layers to produce what we call reservation embedding. So hopefully that embedding would represent all information we have for that specific booking. As we have for each trip a sequence of bookings, so we feed a sequence of such embeddings to the XLNet transformer blocks. In our case, after hypertuning, the best setting we found was 4 XLNet transformer blocks with 4 heads each. You can check the additional hyperparameters in our paper. And then we take the output of such transformer blocks and use a fully connected layer to create what we call a trip embedding, right? Which hopefully would represent everything we know about that trip. And then we reuse the weights of the city embeddings as the output layer to produce scores over all items. Next slides, please. XLNet was initially proposed using the permutation language modeling training approach on NLP, right? In which you select a slice of your sequence, and at the attention level, you change the order of the item. So you're basically corrupting your input by changing the order. In our case, we used the masked LM training approach, which is the one like was used in the BERT framework. So in this example, we have in the first row the input sequence. We have let's say we have five different cities in that sequence. And in this masked LM approach, we randomly mask some items, right? And only make it possible for the network to attend to the other unmasked items, right? And then we sum them with position embeddings, so that because the transformers, as they use a technique called self-attention, they have not a concept of position. So we need to explicitly provide some information so that the network can understand whether the item or the city is the third in the sequence or the fourth. So we sum the embeddings of the input sequence with positional embeddings to provide that information. Then we have a sequence of transformer blocks, and at the end we try to predict the items we have masked initially, right? So this creates a disparity between the training and the evaluation and the inference, right? Because the task is next click prediction. Or next city prediction. We wanna predict what's the next city, right? And we don't have information after that fact. But during training, we allow the network to access future information in the sense that we provide access to the cities that the user has traveled after the one you are trying to predict. So to deal with that disparity between the training and the prediction task, we use the approach that they do in the BERT for REC paper, in which they train using masked LM. But during inference, we ensure that we always mask the last item of the sequence. So in that case, we do not provide access to future information to the network. And yeah, it's able to predict the next items according to this protocol. Next slide, please. So this is a high-level review of our Ensemble solution. We have assembled predictions from models 1, 2, and 3 to generate our final predictions. Next slide. It's ensembling techniques have been shown to be effective at improving models accuracy and generalization. And this is, so we use the k-fold approach for our cross-validation. In our case, the train set was complete sessions, complete sequences of trips, and the test set were sequences that had all bookings within that sequence without the last one, which the one we are expected to predict, right? So the test set are incomplete sessions, and the train set are complete sessions. And we used the test set as we were using k-fold. We managed to use the test set as part of the training set so that we could have some additional data there. And the way k-fold works is very known in machine learning. So for each fold, we use out-of-fold data for training. In our case, we use it both train set and test sets. And then in our case, our metrics, our offline metrics were more correlated with the leaderboard score when we computed the metrics using the train set, because those are complete sequence, complete strips, while test sets are incomplete. So it was not very correlated predicting the last but one, the second to last city to the leaderboard. So our evaluation metrics were computed using the train set for each fold. Let's move to the next one. So this is the algorithm, more formally showing how we work it. So we first split data, we concatenate data from train set and test set. We split in 5 folds. And then for each of the 3 architectures we have presented, we used a technique called bagging. In this case, our bagging was about training the networks with different random seeds. That was the bagging technique we have used here. And for each bag, for each random seed, we did the k-fold approach. So for each fold, we trained with out-of-fold data, and we evaluate on data from the selected fold. And additionally, we predicted the last city of all folds of the test data. So if I use, so each of the folds generated predictions for all 5 folds, and then we use that to ensemble and get and average the scores for each of those folds and bags. And in the end, we assembled the predictions over all architectures. So that resulted in about 75 models. That is 3 architectures multiplied by 5 folds, multiplied by at least 5 bags, which are training on different seeds. Next slide. Here are both the final results, which we have shown before, and also the individual results of each architecture. And if you look at the first column, the single bag CV, that's the average of predictions of each single architecture over the 5 folds. And we can see that the XLNet approach, which uses transformers, was slightly better than the others in this case. But interestingly, the MLP one was very close to the GRU and to the XLNet, and it was much simpler and much faster to train also. So that also allowed us to iterate faster and make improvements on it. So it's interesting to see that even a model that doesn't leverage explicit sequence like GRU and XLNet, it was able to do very well for this competition. In the Ensemble CV, we have the result after averaging the results of 5, 6, or 7 bags, depending on 5, 7, or 8 bags, depending on the model. So in this case, the best one is the GRU. Yeah, it's the most accurate one. So this is just to highlight that the benefit we get by just ensembling predictions from the same model using the same data and just use random seeds. This has been shown to be very effective in many scenarios. And the final ensemble result is we have here our CV using the k-fold strategy, and the final leaderboard, which was about 3% better than the second place. Yeah. So next slide. Yeah, Joey will be talking about this data augmentation approach.
Thank you. Yeah, so a very important data augmentation technique for this computation is training our models using reversed trips. Remember, we are given a sequence of booked cities, and we are asked to predict the last booked city. So we can actually reverse this city sequence and to predict the first city instead. So in this way, our training data size is doubled. And well, when we reverse the trip, we need to carefully modify the features, such as the first city of the trip and the time intervals, and since the last booking, and so on and so forth. This technique is very effective, so it improves all of our deep learning models by at least 0.8%, which is significant in this computation. Next slide, please. For future work, we propose an idea of a second-level re-ranker. This is motivated by this figure 5 on the left-hand side. Remember, our deep learning model can achieve top 4 precision of 0.6, which means for 60% of the samples, the correct answer is actually in the top 4 predictions given by our models. But when we look at the top 20 predictions, so the top 20, the precision at 20 is actually 0.77, which means for 77% of the samples, the correct answer is in the top 20 predictions given by our deep learning models, which means there's a huge potential if we could refine our predictions by looking at the top 20 predictions. We tried to use XGBoost to train a binary classifier with the top 20 predictions, and it shows promising results. Unfortunately, due to the limitation of time, and we have actually only one chance to submit to the leaderboard as our final submission. We didn't take the risk to submit this re-ranker, but we believe it has the potential to improve the model's performance much further. Next slide, please. Our solution is published and shared on GitHub. Please find the GitHub link on the bottom left. And the dependencies of our solutions include cuDF, which is a rapid library to accelerate data frames processing on GPU. We use PyTorch to train our neural networks, and we also use TensorFlow to train the multi-stage, multi-head models. All of the models can be trained using one NVIDIA V100 GPU, which has 32 gigabytes GPU video memory. Next, Gabriel will talk about Merlin. Please take it away. Thank you.
Yeah, so this competition was about recommender systems. And we know that recommender systems are complex in the sense that you have to, you leverage many features from the user, from the user context, from the item. And in general, for recommender systems, you have huge embedding tables to represent the categorical features, like we have for example, we can have an embedding table for the users and for the item, and for top service, that means millions of embeddings there. So one of the so NVIDIA Merlin is the NVIDIA platform for recommender systems, and it's end-to-end from ETL to inference. So this slide is just to showcase that all models we have presented here are able to be put in production using a platform like NVIDIA Merlin. And just to introduce a little, shortly the components, in the ETL side, we have the NVTabular tool, which is backed by the Rapids QDF, Desk QDF. So it's able to load, to do pre-processing on GPU without loading everything into memory. So you can use Parquet or CSV files, for example, as input, and it's very efficient doing that on GPU. Then we have a data loader that has been shown to be faster than the one provided by PyTorch and TensorFlow. And then for the training, you can either use PyTorch or TensorFlow as usual, but we also offer huge CTR, which you can define your model using a declarative language or Python. And it has some interesting features for production settings, like the ability to deal with embedding tables that are larger than the CPU, than the GPU. So it has some approach to distribute the embedding tables and do oversubscription so that the most frequent values, the embeddings of the most frequent categorical values are cached for faster training and inference. And on the inference side, NVIDIA has Triton, which is a very efficient platform for machine learning inference. And for recommender systems, you generally have at least two stages. You have the candidate generation stage, which reduces the number of items you will be considering. And then in the ranking model, you can use more sophisticated techniques that might leverage, for example, more features, contextual features, to produce the final ranking. So yeah, please check NVIDIA Merlin as a solution for end-to-end and GPU accelerated recommender systems. And yeah, that's all we have for you today. And yeah, happy to answer some questions now.
Well, fantastic. That was really great, guys. Thanks a lot for sharing all the details of the competition. In a previous life, I used to work in digital advertising, and it's really helpful and insightful to see this approach taken. And I think for the listeners that are out there, they'll probably have a good understanding that this is a incredibly pervasive technology stack that can be applied in pretty much every industry for a lot of different use cases. This stack of software that you described today sounds incredibly powerful. And I'd like to start with a couple questions leading into this, which is, does this stack of software only work for batch data processing, or can it be easily plumbed into real-time services?
I may take that one. So for the competition, the data set was not that large, right? So in general, you do the pre-processing at one stage, and then you focus in the modeling part. So you can do that cycle incrementally. But real-world recommender systems, you have a large chunk of streaming data arriving. It can be user interactions. It can be trip bookings in the case of booking, right? So you have new data arriving. And in general, you cannot afford to retrain all your model from scratch. So you'd like to maybe do incremental training, fine-tune your model with the fresh data. And yeah, the architecture support that kind of approach. You just need a way to do incremental preprocessing, incremental training. And NVIDIA Merlin, for example, support that kind of training protocol, right? So that you can really deploy such solutions, right? For all of them, you need, during inference, you need to gather some features, and that's usually a bottleneck. So you need a fast feature store or a way to preload such features so that you can, for a given city, retrieve all the features available and feed them into the model so that it can provide the inference. So that's one common concern on productionizing such models.
That's great. How big of a data set would you say that this would be able to scale up to?
So the competition was 1 million rows, 1 million trips only, right? And yeah, but we see that from our customers that we have millions of users, millions of items, and billions of interactions. So that's the scale we face today in real-world recommender systems. And you need a way to load data, to pre-process data without loading everything to memory, right? So that's one key engineering requirement. And we also need to deal with the huge embedding tables we have. So that's what we have focused in the Merlin platform, for example.
Fantastic. How easy would it be to adapt this software stack to make recommendations for things like blog content, where users viewing a website and then you want to recommend the next article they should read, or even to movies, streaming video platforms?
I'll start off. I think the idea of the blog content could be pretty similar in that, a trip would be like a user is at their computer surfing the web and they, viewed this, then viewed this, then viewed this, then viewed this. What are they going to view next? And maybe a few days later, they're on the internet again, and they're doing another quote trip. So I think there's a good analogy between the problems. So you could potentially just sort of swap out, cities with the blogs they're viewing, and you could swap out the idea of a trip with, you know, a session of surfing the web. So I think that could be adapted kind of quickly.
Yeah. I've worked on not movies but on games, video games recommendation, and actually the MLP model was inspired by this. So it is to say that the same kind of model can be used in different settings. And if you remember in the matrix factorization example, I mentioned it was Netflix. So it was movie recommendation. And their model was a subset of the model we presented today. So yes, it can be used by movies. It has been used for movies. But you have to make it work, you need two things. First, you need to recognize the user when he or she comes back, because your recommendation is based on previous, for instance, in previous blogs read or previous movies seen by the user. So if you can't track users, you need a different way to make recommendations. The second one, and it was clear for games where at a point, Fortnite is like 40% of all game session in the world. You must balance your system so that it recommending the most popular game or most popular blog or most popular product is likely to give you a good accuracy. If what people want to see is very imbalanced. So you need to balance this with some diversity. So when you recommend products or whatever, if you don't care too much, you only recommend the most popular. And you need to balance this a bit with diversity. So if you go back to the video, you will see that getting embeddings of every city, every product, everything gives every product a chance to be recommended.
Fantastic.
Yeah, maybe an additional comment is that depending on the domain you're applying the recommender system, you might have additional information, right? In this case, we had only besides the city, which is the item, in this case of the recommender, we have the country and nothing else. But in general, you have more information available, right? For example, when you are recommending articles or news, you have access to the text. So you can use some neural network to generate a dense representation of that textual information and use it to recommend, right? And it's especially important in the case of the news. Most user interactions are on news, on fresh news, fresh items that have been published in that same day. So you have not much time to learn for which person you should recommend that news piece, because collaborative filtering techniques expect you to have like hundreds of interactions on the same item, in this case a news article, so that you can learn a good embedding for that news article and start recommending them. So in such scenarios, it's very important. This process is known as the cold start problem recommender systems, right? How to deal with fresh users or fresh items. So leveraging site information like the textual content, or you can, for movies or blog posts, you might have access to the image, so you can generate an embedding from that image. So this site information is useful for you to be able to recommend an item, even if it's fresh, if the model, and even if the model was not trained to predict that item, just because you have useful site information.
Great. So when you guys are working on these competitions, do you have a preference for working on like a GPU-enabled desktop versus working in the cloud or on a cluster? Is one easier than the other for you? Jean-Francois, I think you are muted.
Sorry. Yeah, we were a bit privileged at NVIDIA because we have access to good GPU-powered workstations, the DGX stations. So when I can fit a problem on it, it's much better than any cloud resource, because you have no latency, you have full availability of the machine. But having access to GPU on the cloud, and we have an internal system at NVIDIA that we'll use, but base command. It's really, it can scale. So in this competition, we did not need much compute resource because the problem was small. But when you train these models on much larger data sets, having the ability to scale using cloud resources is very important. So it's a matter of size of the problem. If it's small enough, running it locally on a GPU is the best for me, at least.
Great. And given that this was a group effort, were there any tools you used for collaboration? Or are there any tools you would suggest people consider using to keep everyone in sync with the latest data set, latest models, etc.?
Use it Slack, GitHub. What else? Google Sheets and.
Do you use anything to keep shared models or any place other than just a GitHub repository? You're muted, Jean-Francois.
Sorry. We keeping model diversity is very important. That's something people may not get, but we got a huge boost when we ensembled our models, even if they had similar accuracy, their ensemble was much better. It's because they are different. So not sharing too much code is a good thing if all you care about is the best possible accuracy. So it's not, this was a competition, so it's a proof of concept. It's not like developing a model for production system, in which case you would want to rebuild it with Merlin and share code and use sound software development practice. But here the goal was to get the best possible predictions, and the software quality was not at all a measure. So for this, Slack and loose collaboration, loose connection is the best, I believe. But I would not recommend this way of working for software development projects.
What about from a data preparation feature engineering standpoint? Was there any collaboration around getting the data set prepped and ready?
No, we exchange ideas of features more than code to do it, if I remember well. Do I remember well? Maybe I'm wrong.
Yeah, that's correct.
Yeah, actually, so this computation is special in the sense that we only have 2 weeks to work on it, and the data size is not large at all. So for the feature engineering, I believe Jiba actually did a wonderful pre-processing and cleaning and engineering job. So basically, he single-handedly cleaned the data set, create the most important basic features, and share it across all the team members. And based on his process, the data, we just built deep learning models individually.
Yeah, it's right. Jiba is not on the call here, but he could have been.
All right. Well, fantastic. That's all the questions that I have. Chris, Jean-Francois, Jiwei, Gabriel, thank you very much for spending your time speaking with myself and all the viewers today. I think we all found this conversation enlightening and educational. To all the viewers, thanks so much for spending part of your day with us and taking the time out of your otherwise busy schedule to enjoy this episode in the Grandmaster Series. I'm Jim Scott, and I'm happier knowing I can relax a little more because my streaming video experience may get even better based on improved power of recommendation systems. Have a great day, and may all your data science be accelerated.